A very good afternoon once again. So we'll pick up things from where we stopped last time on signals and systems. So this will be a quick recap, and then we'll emphasize a few details. Good. Now to begin, I would love to quickly review the impulse response and convolution of the LTI systems. Impulse response and convolution of LTI systems. So you will recall that an LTI system paired with an input, say S of t, say this is an LTI system, paired with an input S of t, and characterized by, say, H of t, that is the system itself, is characterized by some parameter. This is the LTI system characterized by some parameter H of t. Then we produce an output Y of t such that the impulse response of the system H of t convolves with the input S of t. Now, H of t is the impulse response of the system, and it is a property that characterizes the system. Okay? And now, this impulse response, H of t, is easier to evaluate in the frequency domain, which gives us H of s. Okay? So H of s in this case is referred to as the system function, like we mentioned earlier, or better still, the transfer function of the system, and is the frequency domain representation of this impulse response. So we have that H of t can be transformed to H of s and vice versa between the different domains. So by definition, what is H of t? Now we see that H of t is the output of an LTI system when it is fed with a Dirac delta function, dt, for which the system itself is an LTI system. So this is where we are gradually coming to. So we know the unit impulse, the Dirac delta function, has a finite amplitude and an infinitely large area. Now, how is that? Now let us look at this. Let's look at this. The delta function, or the unit impulse, we have an infinite value at t equal to 0, and then at 0 otherwise. So it means that the Dirac delta function is of this form, where this is t, and this is the value at 0. Now, let us consider, this we already explained earlier, let us consider a rectangle, for instance. Okay? This is a rectangular function, having the amplitude of, say, 1 over 2a. Okay? Now, we know if this is negative a and this is a, so it means that this length is going to give us 2a, right? This a, this is a. So the area under this curve, this area, is the same as length times breadth, right? Which is going to give us the integral from negative infinity to positive infinity, y of t, where this is y of t, dt. Now, since y of t in this case is defined as 1 over 2a, taking the limit or range from negative a less or equal to t less or equal to a, then is 0 otherwise. So if we integrate this parameter over this limit, we should get the area. So this will give us the integral negative a to a, 1 over 2a dt. So this is a constant, right? So it's going to come out 1 over 2a integral negative a to a dt. So that will be 1 over 2a t minus a, which will be 1 over 2a into bracket a minus a, which will be the same as 1 over 2a into bracket a plus a, which will be the same as 1 over 2a into bracket 2a, which is equal to 1. So it means the area in this case is 1, right? Now, if this is true, now for us to get unit area, then it means that as we shrink this length, let's change this color. For us to get unit area, now if we reduce this length by say half of this, so it means that this will be negative a over 2, then this must scale up. The height of this must scale up to some value 1 over a for us to do that, such that we will now have a, so this length here will be a, then the height will be a. So recall length times breadth will be a times 1 over a, so that will give us unity. Now you see that as this length shrinks and tends towards this axis, the x-axis of 0 value, then you see that it continues to extend to infinity, okay, till we have just a single impulse here extending to some infinite value at 0. That's how we get the unit impulse response. And you could validate this also. If we integrate 1 over a from negative a to a, that's going to give us 1 over a t a minus a, that's 1 over a into bracket a minus a, which is 1 over a, right? Is that? Over 2, this over 2, 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 right? So that will be a plus a, right? Isn't it? It will be a over 2 plus a over 2 will be a, which is equal to 1. Yeah. You know? So, and we know that this unit impulse response is the input to an LTI system for which the output is h of t, which is the impulse response, okay? Now, if this is clear, okay, we now see that if the integral of Dirac delta, the t, is equal to 1, then 1 is the same as a unit step function, okay? And if we differentiate the Dirac delta, the first order derivative of the Dirac delta is the same as a doublet, okay? Doublet function. Now, this unit impulse response is very vital. It's a very useful instrument in signal processing. Now, should we decide to shift this response in time, okay? Decide to shift it in time. Once we apply this to a particular signal, then we could generate a digital equivalent of a continuous time signal. Now, this is what I mean. So, given this unit impulse, so this is 1, this is Dirac delta, and this is 0, this is t. So if it's time shifted, so it means that this is my axis here, it's time shifted, t minus t sub k, so it's shifted to some time t sub k. So it means that we are going to have, oh my goodness, we are going to have this impulse at this point. This is 1 at t. Okay? Okay, so now, when a signal S of t is now multiplied by this time-shifted version of the unit impulse response, then the signal is seen to be shifted by time t sub k, such that the signal therefore assumes its value at that time instance. So if, for instance, we have S of t as a signal, I will multiply it by the time-shifted version of the impulse response, you now see that this signal we now assume its value at this t sub k. You see, S of t, we now change to S of t sub k, Dirac delta t minus t sub k. And don't forget, this component is unit value. Okay? So the signal automatically becomes S of t sub k times 1, which is the same as S of t sub k. Okay? So if, for instance, we now have a signal, say this, and then we have a comb function, this. Once we multiply this, then we are going to have something like this, such that we now have this signal in this form. Now, if this is t, let's say t sub 1, t sub 2, t sub 3, t sub 4, t sub 5, for instance, then it means this is now t sub 1, t sub 2, t sub 3, t sub 4, then probably here t sub 5. So this now, if this is our input, then this gives us the output y of t. So technically, it means that S of t sub 1 is the same as S of t sub 1 times the shifted version of t minus t sub 1 occurring at that time instant. Then S of t sub 2 will be S of t sub 2 occurring at this time instance t minus t sub 2. Then also S of t sub 3 will be S of t sub 3 times the time shifted version of the impulse response at time t3, on and on. So since the signal S of t could be disintegrated into a set of impulses. Now you see this signal have been disintegrated into some set of impulses, which are S of t sub 1, S of t sub 2, S of t sub 3 to S of t sub 5 in this case. Then the response of the LTI system to an arbitrary input signal is simply the sum of this scaled version of the signals. You now see that this is now S of t sub 3 is a scaled version and the time shifted version of the signal. So by the time we add up all of those components, that is
Mr. Inkus,
y of t will now be the same as S of t sub 1 plus S of t sub 2 all the way to S of t sub 5 in this case. Now, once we do this, we now see that this is the convolution of the signal. Now, how is that? Let's write this. Now, we have been able to establish that by way of applying the unit impulse response on this signal, we have been able to disintegrate this continuous time signal into some samples, such that this sample now is S of t sub 1. This is S of t sub 2. This is S of t sub 3. This is S of t sub 4. This is S of t sub 5. Now, Y of t will now be the sum of all of these signals, which is S of t sub 1 plus S of t sub 2 plus S of t sub 3 plus S of t sub 4 plus S of t sub 5. And mind you, this is the same as saying S of t sub 1 Dirac delta t, which is a shifted version, plus S of t sub 1, that is this, then these two, Dirac delta t minus t sub 2, plus all the way to S of t sub 5, Dirac delta t minus t sub 5. Okay? Now, if this is what it is, then it means that, recall that the sum of a signal, or that's more like taking the average of that value, is the same as the integral. Okay, so when we are using summation in the discrete equivalent, we are using integral as the sum. Okay, so it means that for the continuous time signal, Y of t can be represented in this case as taking a limit from t sub 1, the integral, taking a limit from t sub 1 to t sub 5, S of t sub k, Dirac delta t minus t sub k. So this is the representation of what we've been talking about. Okay? And this expression is referred to as the convolution in the time domain. This is the convolution in the time domain. Okay? And now, in the, okay. Now, if this is the time domain equivalent, then how about the discrete equivalent of this? We already know that the integral is the same as the sum, right? So from the foregoing, based on what we have already established, if the convolution in the time domain, convolution in the time domain is the same from our previous example, same as the integral, taking the limit from t to 5, t1 to t5, S of t sub k, and the time shifted version of the impulse response. T. Then the this therefore gives us the basis for the generalization. Okay, so in general, the continuous time signal is the sum of the scaled and time shifted impulse response or impulses. So general, any continuous time signal is the sum of the scaled and shifted, these are the shifted impulses, unit impulses given by y of t being the same as this to this, s of tau, t minus tau, tau. And the discrete time signal, and as such, any discrete time signal is the sum of the scaled and shifted unit impulses given by y of n being the same as the sum for k taking on values from negative infinity to infinity, s of k, shifted version, n minus k. So you can see that this is the scale, these are the scale parameters, while these are the shifted parameters. Good. Now, before I go into some other analysis, it should be noted that convolution helps in signal sampling and digitization, okay? So just like we mentioned earlier, you see that, say we have this signal. If we multiply it with a comb, then we can say, well, we have something like this, and then this gives us something like this, okay? So you note that in the frequency domain, sampling of the original signal is the same as the convolution of the original signal with the comb function, having repeated peaks at the sampling frequency. So I want to write that. In the frequency domain, sampling of the original signal is the same as the convolution of the original signal with a comb function. This is the comb function here. With a comb function having repeated peaks at the sampling frequency. Okay. And then the quantization process therefore follows directly from the sampling or from the signal sampling in order to convert a continuous analog signal to a digital signal. So we want to convert analog to digital. So it follows directly that we first sample. After sampling, then we move on to quantization. So hence, the signals are quantized by mapping continuous finite values to a smaller set of discrete values so that an analog signal is digitized, okay? So at this point, it should be noted that the sampling theorem specifies the minimum sampling rate at which a continuous time signal needs to be uniformly sampled so that the original signal can be completely recovered or reconstructed by the samples alone. So this is more formally represented as the Shannon sampling theorem, okay? And the Shannon sampling theorem states that if a continuous time signal contains no frequency components higher than WS, for instance, then it can be completely reconstructed or determined by uniform samples taken at a rate f sub s samples per second, such that f sub s is greater or equal to 2W, where W is the maximum frequency of the signal. And then f sub s is the sampling frequency. So it means that, and W is the maximum frequency of the signal. So it means that the sampling frequency must be greater than or equivalent to twice the maximum frequency of that signal for it to be completely reconstructed or recovered. And in terms of the sampling period, we can restate the sampling theorem as T being less than or equal to 1 over twice the maximum frequency, where T is the sampling period, okay? Where T is the sampling period. So why this? We want to transmit a signal, but it will not make sense transmitting a signal if we can't reconstruct the signal. So now that I'm talking, you can hear me clearly because the signal being transmitted via my voice activities is completely reconstructed and recovered at your end, okay? And you should know that the band-limited signal is one in which no frequency component is above a certain maximum frequency. So usually we have band-limited signals to be of this form, okay? So the amplitude is finite, and then here we can say this is the cutoff frequency. Okay, let me shift this a bit. I want to shift this from the axis. Shift that from the axis. Let's shift this from the axis to say this is twice this minus this, then that. So this is a bandpass filter or spectrum. It's equivalent to a bandpass filter or spectrum, while this is more like a low pass filter or spectrum, where this is W and this 0. So you should also note that the Nyquist rate is the minimum sampling rate allowed by the sampling theorem. So when f of s is equal to 2W, then this is the minimum, you know, that can be allowed for perfect reconstruction of a signal. And we'll call this Nyquist rate. Okay. Okay. Now that we have mentioned that, we've jumbled a whole lot of things together. So I think it would be good to mention another important point, you know, some techniques used for the conversion between discrete time systems and continuous time systems. Okay. So I think number one I want to mention here is impulse invariance method. Impulse invariance method. Okay. So and this method, better still, the impulse invariant method converts analog filter transfer function to digital filter. Okay. This converts analog filter transfer function to digital filter transfer function, such that the impulse response, like we already mentioned, is the same. That is invariant. Okay, the impulse response is the same at the sampling instant. Okay. And then we have, by mathematical representation, that Z, being the Z transform, is the same as ST. So this is the discrete domain. This is the continuous. This is the discrete domain. What is the continuous domain? Okay. So that's one. So let us look at another method, the backward difference method. Backward difference method. Now, it is also referred to as the approximation. The approximation by derivatives method. Okay. And it is used to achieve stable digital filters. Okay. Using analog filters. Now, in this case, the Z transform is used to convert differential equations to difference equations. Okay. Differential, which is a continuous domain, continuous time domain, differential equations that is analog filter into difference equation, which is digital filter. Okay. And here we have the S domain is the same as 1 minus the inverse Z transform over T, while Z is the same as 1 over 1 minus ST. Okay. Now, let us look at one other method for converting between continuous time systems and discrete time systems. That is the bilinear transformation method. Bilinear transformation method. And this method maps the left half of the complex S-plane to the interior of the unit circle. We're going to see this very soon when we talk about, when we try to figure out the stability, you know, in terms of, for the transforms. Unit circle of the Z-plane. So hence, filters designed in the continuous time domain that are stable are converted to filters in the discrete time domain that preserves that stability. And here we have that from the S domain,
My image just
C,
for
1 minus Z inverse over 1 plus Z inverse. And then we have Z also can be transformed to the continuous time domain, T over 2 S, this is 1, divided by 1 minus T over 2 S. Okay, so these are the three methods we'll just make mention of for now, for the sake of our time. And then we now see that in coming back, let's come back now to the convolution talk. Then, okay. So, meaning if we have this system in the time domain is an LTI, and then we have H of T, or better still, in the discrete domain is LTI. This is H of N. So once the impulse H of T, for instance, is known, then the system response to any input can be evaluated by convolution. So if H of T or H of N is known, then the response of that system could be evaluated. Now, we now see that, say, Y of T fed into an LTI system characterized by H of T, Y of T, sorry, S of T rather is the input, Y of T is the output. Then Y of T is S of T convolved with H of T. So Y of T will therefore give us the integral taking limits from negative infinity to positive infinity, S of tau, H of T minus tau d tau. So in a similar vein, for a discrete time sum, then Y of N will be the same as the sum of these parameters taking on values from negative infinity to infinity, S of K, H of N minus K. So here you know that convolution produces an output that is the sum of the scaled version and shifted impulses, like we mentioned earlier. So what are the steps required for convolution? Good. So this is very important. So steps required for convolution. So as you already know, Y of T is the same as S of T convolved with H of T, which is the same as integral negative infinity to positive infinity, S of tau, H of T minus tau, tau. And now The first point here is that the impulse response is time reversed. So h of tau is time reversed. And once we do that, so the first point here is that h of negative tau is time reversed. So it means it's reflected about the time scale. Then afterwards, we perform time shifting. So perform time shifting on h of negative tau. And once we do this, we are going to get h negative tau minus t, right? We're actually performing time shifting on tau. So this is now going to be the same as h of negative tau, negative t. And this is going to give us h of negative tau plus t, which will be the same as h of t minus tau. See? Now, we are now going to multiply the input signal and the shifted impulse. So the next thing is multiply the input signal and the shifted impulse. Okay? Now, you are going to do this for all the values of tau and t fixed at some value. Then, once that is done, then you integrate the product. Integrate the product of s of tau and h of t minus tau for all values of tau and t also to produce a single output, y of t. So this will give us y of t. So we're going to repeat this over the time interval. Now, well, there are some examples in the video, and I will just look through a simple example. And we already know how to convert let's say the convolution of two rectangular pulses of equal duration will give us a triangular function. And that is when we try to convolve, say, this rectangular function with another rectangular function. Say this is T1 and this is T2, this 0, this 0, where T1 is the same as T2. So they have equal duration, okay? Equal duration. So the output is going to give us a triangular waveform, okay? It's going to give us a triangular waveform. Now, what if we convolve two signals of two rectangles of different duration? Okay, T1 and T2 are not equal. T1 is less than T2. Okay, so this is going to give us some kind of a trapezoidal signal. Okay, the formulas for all of that is already in the lecture notes. So, but there's one part I want to just explain so we don't get confused, which is the convolution of a discrete time system or signal, okay? So let us consider this example where we have S of n to be given as, say, this is 1, this is minus 1. So the magnitude of this is 2. So on the scale, this is 0, 1, 2. This is n. And then we are also given h of n, which is the same. This is 0, 1, 4. This is 1 here. Then somewhere around here, so this is 2. So this is n. So here we have 0, 1, 2, 3. So if we assume this is a system of this type, S of n, fed into the system, and then we have our output, then we want to resolve this. So we know that the convolution is given by y of n being the sum, k being the same as negative infinity to positive infinity, s of k, h of n minus k, okay? But this time we have s of n here, not s of k, okay? So we know that this is the same as writing this k negative infinity to positive infinity, s of k, h of minus k, minus n. We have written the same thing here, okay? So this is minus k minus n is plus. So we have not done anything different here. So this now, again, is the same as writing the summation of k equal to negative infinity, positive infinity, s of k, h of minus k plus n. Yeah? Now, if we add n to both sides, or say, no, we can't add n. We want to eliminate this n. I want to have just k here, so that we're able to shift the signal by this impulse response. Now, if we subtract n from here, we're going to have negative k. So it means that this process will reduce to something like k might equal to negative infinity, taking off limit from negative infinity, sum of these parameters. So that'll be x of k minus n. So minus n. So we'll do the same thing here. Minus k plus n minus n. Right? So once we have this, then we are going to have summation, k taking on negative infinity to positive infinity, s of k minus n, h of minus k. So you now see that the impulse response here is time reversed, right? While the signal is shifted. So now that we have this, we can use this as our basis for convolution, okay? Now, we are going to make another interesting assumption here. We are going to assume that S of n is the same as S of k, such that h of n is the same as h of k. Now, once we are able to make that assumption, then it means that we are going to change the scale from n to k. Okay? Now, if that's that, then I can wipe this and begin my analysis. So can begin our analysis such that this now changes to k. Okay. So this applies. So for us to now achieve this, then I'll have to replace this. So if we shift this now, the time reversal here, it means negative 0, negative, this will become negative 0, negative 1, negative 2, negative 3. So all of this will move to the left. So h of minus k will now give us 0. Will now give us 0 for 0, negative 1. This is 4. This is 1. Negative 2. This is 2. Negative 3. Yeah. Now, is that clear? Now, if this is clear, so it means that we won't be using this parameter. So this is what we are going to be using based on this and this. So the first point here now is for us to begin to evaluate these parameters. When n is equal to 0, then we are going to have y of 0, because this whole process now is the same as y of n, right? We're going to have y of 0, which will be the same as s k minus 0, that will be k, then h minus k. So this is what we're going to evaluate at that point. Then for n equal to 1, we are going to have y of 1, which is equal to s of k minus 1, then h of minus k. When n is equal to 2, we are going to have y of 2, which is s of k minus 2, h of minus k. Then n equal to 3 to be y of 3, which is equal to s of k minus 3, h of k minus h of minus k, all the way. Okay, so I'm going to do the first one, and then you look up the video to follow up on the details. So now, if we want to do the first one, so for n equal to 0, so y of 0 is going to give us this expression here, 0. Now, okay, before I plot it, let's do the needful. Now, at this point, is the same, right? So we are not adding anything. So we're having exact same. So it means we're having this multiplied by this. So since it's the same here, at 0, at terminal of 0, s of k is 1. So that's the magnitude. And here it is 0 times 0. So we're going to add at 1, it is minus 1 for s of k, times at minus 1, it is 1. Plus, now at 2, there's no 2 here, so there's no overlap. So it's 2, the magnitude is 2 times 0. So here, no overlap. So we won't do anything there, okay? So we are going to add up this. So 1 times this, sorry, at 1 also, there's no overlap, sorry, because this is minus 1. So at 1, there is no overlap because there's no 1 here. Because this is supposed to be 1, this is supposed to be 1, 2, all the way. So at 1 here, it is 0, right? It is 0 because there's no parameter at 1, there's no parameter at 2. So between 1 and 2, there is no overlap. So we have just this element where we have overlap between 0 and 0. So and 1 times 0 is 0. So this parameter here is 0. So y of 0 is equal to 0. So when we also begin to plot our y, so we can pull off the axis, okay? So we begin to plot it also, okay? We can pull off the axis that long, okay? So it's either to the negative or to the positive, so I don't know. So I have 0, -1, -2 all the way. Then we have 1, 2, 3, 4. So on the axis. So right now at y0, we have 0. So it means that's what we have here. 4. At this point. Oh, no. What am I doing? This is 0, right? So at this point, we have 0. That's the first signal point there. Okay, so let us try the second one at n equal to 1. At n equal to 1. So let's write this. At n equal to 1, we have this. So we have to design this signal. So k minus 1. So 0 minus 1 is minus 1. So we are going to be having on the axis here. On the axis, when n is 1, so for the n, for the x, yeah, k minus 1, okay, for this, okay? So we want to do this. So here is 0 minus 1. So 0 minus 1 is minus 1. So we have a minus 1 value. 1 minus 1 is 0. So we have 0. 2 minus 1 is 1. So we have 1. Okay. So we are going to be having something like this for this. So at this point, this is 0. Then at this terminal here, we have minus 1. Then at this point, we have 2, right? So this is what is going to multiply with h of minus k. We know h of minus k. So our y1 at this time will be at minus 1, we have overlap. So that will be 1 times 1, right? 1 times 1. At 0, we have overlap too. That's minus 1 times 0. Then at 1, we equally have no overlap. So that's 1 times 0. So no overlap. Okay, no overlap at 1. So we only have overlap at this point. So this will be 1 times 1 is 1 plus 1 times 0 is 0. So it's equal to 1. So y of 1 is equal to 1. Okay, so that now brings us back to the output here. So at point 1, we have 1. Output is 1. You get it? So this is how we are going to continue to populate this. By the time you solve up to 5, you will now see that at point 1, we have this. Then at point 2, we're going to have the output of 3. Then at 3, we are going to have 0. Then at 4, we're going to have 6. Then at 5, we are going to have 4. So at 6, no overlap all the way. So with this, we are able to conduct discrete convolution, okay?